Hi everyone, we are Team 11 and our project is focused on compressed air systems and is sponsored by Collins Aerospace. My name is Emily Beleza.
My name is Ben Flax.
My name is Kira Dabrowski.
And my name is Danielle Del Piano.
Compressed air is commonly the most expensive utility for industrial plants. This is because it takes a large amount of electricity to produce a small amount of compressed air, and a large amount of compressed air goes wasted in industrial systems. Close to half of all compressed air produced will leak out of the system or go unused. Compressed air is a valuable resource in many industries, including at Collins Aerospace. The Collins Aerospace plant compressed air system mostly simulates the pressure different aircraft components will endure during flight. At the plant, centrifugal, reciprocating, and rotary screw compressors are in use. For the purposes of this video, TA-labeled compressors are centrifugal, XLE is reciprocating, and SSR is rotary screw. The problem we are facing with Collins' system is there are many inefficiencies that are causing major expenses to the company. These inefficiencies are leaking throughout the system, as well as compressors that are nearing their end-of-life expectancy. In addition, the plant does not have a heat recovery system to cut heating costs and increase efficiency. Finally, the plant's data collection system is cumbersome with many broken sensors causing unreliable operational data in bulk. Collins is also looking to size up their system in the future. The design problem is to propose improvements by looking through operational data from the system and drawing reasonable conclusions. From here, recommendations need to be made using a simulated model and process control principles to improve the system's deficiencies.
This figure shows the system as represented by our equation-based model. We developed it by starting with a simple mass and energy balance for the compression and storage of dry air. By assuming that the air behaves as an ideal gas and has a constant heat capacity, the system can be modeled by these equations. Next, we program the equations to be solved in MATLAB. The model works by taking different user inputs for customizable variables, like the duration of the trial, the inlet temperature, and the mass flow rate. Aside from user inputs, other variables in the system, like machine efficiency, amount of heat removed, and set pressures, are also easily adjustable. For the end-use pattern, there are currently two options: a constant flow rate, which could be used to model a leak or constant usage, for example during an extended equipment test or tool operation, and a cyclical flow rate, which simulates intermittent usage. Once an option is selected, the program prompts the user for one or two more inputs. Then the program completes the calculations using a differential equation solver with event detection settings to model a simple pressure controller. On the left is a sample user input for a simulation. The output of the model is two plots, one showing the temperature and pressure over time, and one showing the energy drawn by the compressor and total power consumption.
The current baseload requirement at the plant runs a consistent outlet pressure around 118 psi. However, at times of high demand, the required mass flow rate can increase by up to 300%. This baseload is covered by a combination of compressors. In order to avoid overwear on any one piece of equipment, the combination of compressors covering the baseload changes periodically. Generally, the baseload is satisfied by the SSR1, SSR5, and SSR6 rotary screw compressors, with the remaining energy being supplemented by one of the XLE reciprocating compressors. To satisfy the baseload condition and plant demand, one of the SSR compressors runs at full speed, while the other compressors cycle on and off to satisfy the remaining pressure requirement. To more efficiently cover the baseload at Collins Aerospace, we will use our developed model to recommend the best compressor combinations and offer advice regarding which compressors that are at the end of their operating life should be repaired versus which ones should be replaced.
We used these equations to estimate the cost of the compressors in our cost estimation model. These equations are from the textbook Chemical Engineering Design, Principles, Practice, and Economics of Plant and Process Design, 2nd edition, by Gavin Teller and Ray Sinnott. The first equation is the capital cost estimation where A, B, and N are all constants from the book and S is the driver power. To find the total cost of installing the new compressor, we use the second equation where F is a constant from the book. We use the last equation to estimate how much the utilities of each compressor would cost. N is the number of hours the plant is running, E is the energy used, and C utility is the cost of the utility. We estimated the cost of getting a new compressor and fixing the old compressor. Collins can also use this cost estimation model to make any decisions about their compressors in the future. We focused on triple point sustainability. Triple point sustainability is a compromise between the environment, the economy, and equity. The biggest part of improving sustainability is by decreasing emissions from the compressors. This would decrease the cost for Collins while also improving the air quality, which would help both the environment and the community. The biggest way to reduce emissions that our group recommended is by completing a retrofit or a redesign. A retrofit would cause less emissions immediately, whereas a redesign would be better long term. We also proposed the idea of a heat recovery system, which could increase efficiency and decrease the emissions.
We hope that you enjoyed learning about industrial compressed air systems with us. We want to give a special thanks to our faculty mentor, Dr. Stuber, and to our sponsors at Collins Aerospace, Paul Johnson and Joe Mortimer. We are grateful for all of the guidance and support that they have given us during the past several months. Thanks again for watching our video, and please feel free to reach out to us with any questions.